All right, let's check our audio. Where is our channel? Canali. Check. Wow, my audio is so wonderful. Such a wonderful audio. I love it. I love my audio. Finally, I have an audio. Finally, my audio doesn't drop every time I log in. Oh my god, I love looking at it. It's 100% audio. 100% audio is the best. All right, ladies and gentlemen, let's continue. We need to write this paper. Here's the paper. Look, I don't know how to explain this. The best thing I think is just to take ChatGPT, its interpretation. It says constancy of the speed of light. That's how it's interpreting this quote. Describing a key principle of Einstein's theory of relativity in the context of special relativity, the speed of light in a vacuum, denoted c, is fundamental constant of nature and is approximately meters per second. Here are some important points related to this concept. I can quote this whole thing. This is what ChatGPT gathered from the internet. That the constancy implications, the constancy of the speed of light leads to several counterintuitive implications such as time dilation and contraction. We can show time dilation instantaneously, but I don't want to do this in this paper. Invariant speed, the invariance of the speed of light is central to the structure of space-time. Relativity implies information or matter can travel fast. That's not true. I don't care. Relativistic effects. Constancy of the speed of light. Observers moving relative to one another will measure different times and lengths for the same events. This is because the space-time intervals. Look, it's really not important. All we need to do is maybe just take this constancy of the speed of light. Speed of light in a vacuum is the same for all observers regardless of the motion of the light source or the observer. Einstein doesn't say that, but fine. This principle was one of the two postulates that Einstein used to develop his theory. We don't need that. So just the first one. No? So I can't do... Okay, I can. All right, let me... Just this. So the speed of light in a vacuum is the same for all observers regardless of the motion of the light source or the observer. And what did Einstein say? Light is always propagated in empty space with a definite, and they say in a vacuum, definite velocity c, which is independent of the state of motion of the emitting body. Assuming there is an observer in this discussion. So I don't know if I should quote ChatGPT. My intuition is... One second. My intuition is not to quote. Not to quote. My intuition is not to quote ChatGPT. What happened? We have somebody with us. Sinas. Oh, Sinas. Very nice. Hey, what's up? Your mic is off. You're muted.
Yeah, my mic was off. Yes. Okay.
Mm-hmm.
Hello.
Hi. Okay. How are you?
So, did you figure the other thing?
What?
Did you figure out that experiment that I sent you? That I cannot say the names of the people. The German.
Gerlach. Stern and Gerlach.
Yeah.
I thought I did, and then I started listening to different lectures about it, and I don't. But I no longer view quantum mechanics as confusing. It's the nature of the beast. What I was thinking is
because you have like a physical way to visualize it.
Not really.
So it's no longer just
a little bit. I'm beginning, because I have the ether in my mind. I am beginning to be able to visualize different things, but not completely, not everything. And at the end of the day, it's just the nature of the beast. You know, at this point, I'm not going to be right, even if we completely understand the behavior of the ether and how it gives rise to all the forces. Then the question is, okay, but what is the ether? What is its nature? Where did it come from?
Yeah, there are some good hypotheses for that. I think even that famous physicist Dirac had a good hypothesis, which was like basically he called it the Dirac sea, which is basically like a sea of dipoles. So a sea of positive and negative charges that are in neutral state for the most part, so they don't really affect matter too much.
Wait,
But your view is a bit different because it includes gravity.
wait,
His view
Dirac?
was more to try to explain electrical effect and so on,
Wait, hold on. You
and
saying,
mass as well.
wait,
Hmm?
hold on. Did you say Dirac talks about ether?
Yes, yes. Dirac had his own more or less ether theory that he didn't call ether. He called it Dirac sea.
Mm-hmm.
Yeah, it's never been like 100% agreed amongst all, even the famous scientists and the famous physicists, that data doesn't exist. And in fact, if you look at it, almost pretty much every physicist says that the vacuum is not empty and so on. So it's just, yeah, they can't really resolve their ambiguity. So they have these weird views that you can't really tell if they believe there's something in the vacuum or there is not. It's weird.
Yeah, it's
But yes,
not.
Dirac is a good example of someone who has his own hypothesis. And I think it makes a lot of sense. I think,
Can you get
because if
me?
you want to explain electrical effect, it needs to. Yeah, I can hear you. Now I
Yeah.
can. Did you stop for a while or not? No, because if you have to explain electrical effect, it has to be like a sea of charges. Like it's. I mean, it's kind of intuitively the first thing you would go for.
Mm-hmm.
Are you there?
Yeah, I'm here. I'm having a very hard time hearing you. Or like your mic, there's
Really?
echo. Yeah, it's
You know,
very, your mic is
is it
very
better now?
bad. We'll have to see. I
Yeah,
don't
I'm on my
know.
phone.
Oh, yeah. I'm having to press my
Uh,
headphone against my ear to understand you. Like
yeah.
my headset is terrible. I'm gonna have I have I have 20 headsets on my table that all one is worse than the other. I don't know what to do. And I got this really good one, and as soon as I opened it, it broke. It's so flimsy.
I'm going to I have the computer here. I'm going to try to go to the computer.
The computer,
But
that's
the problem
the.
is I have limited internet, and I need the internet to work still. So
Wait, your
yeah,
internet is your internet is not working?
yeah, because I'm not at home, so I have like an internet package, so to speak. But it's like there's not a lot of it, and still has to last for the weekend. So I joined on the phone because the phone is like I don't know, there's less internet consumed, I guess. I don't know. But I will join on the computer. Wait a minute.
Okay. Oh my God. Talking to every person, everyone has such terrible audio. It's like one is worse than the other. I don't know who has the worst audio. I thought I have the worst audio. Jesus Christ. And now I have this problem with the fan. I cannot turn it off. I cannot turn the fan off. It's drying my skin. And it's windy in this room now, and I can't. It's making noise, so I'm having a hard time hearing. Such a nightmare. Everything is so nightmarish. Okay. Anyway, I was going to look at this. I don't know what to do with this. Einstein's. This is just a quote. So let's start over. So proof of Einstein's special relativity's second postulate using a rubber ducky in a bathtub as a model. let's remove this. Let's just, it's bad enough that we're proposing that we have a proof. And by the way, this should be centered. How do you center this? Proof of Einstein's special relativity second postulate. How did Einstein title his paper? Oh my God, Jesus, help me. On the Electrodynamics of Moving Bodies by Albert Einstein. Did he misspell it? Einstein. June 30th, 1905. Oh, we need to put a date, and we need to say by who. Oh my God. Okay, so this is okay. Now we want, this is title, subtitle. Okay, and this needs to also be centered. This is going to be, wait, what do we have first? By who, and then the date. Okay, so by Mr. Slave, and the date, well, this is heading 1, and where is this? Today is, one second, what is today's date? One second, let me see, somebody wrote us something. Send us restarting the computer. Okay. Take your time. All right. The question is by Mr. Slave. This is subtitle, and then the next one is heading 1. It's going to be, I think, too big. I think this should be the subtitle as well. So we should just say subtitle. So today is August 16th. August 16, 2024. Okay. Proof of Einstein's special relativity second postulate. So we need to start with, in his paper, Herr Albert Einstein,
Still going to take a bit on the computer. I don't know what's going on here.
Because
the internet's not working.
It's fine. I'll just press my headphone into my brain. It's fine. I'm used to suffering.
Okay.
Anyway, so yeah. Everybody's audio is atrocious. By the way, how is my audio? Can you hear me well?
The audio is perfect.
My audio is perfect. Well, thank God. Let me hear. I want to hear it. I'm so excited that I was finally.
Can you hear me well? The audio is perfect.
My audio is perfect. Okay, one second. I just turned off my iPhone.
Oh, thank God.
Let me hear. I want to hear it. I'm so excited. I was finally able to figure out my audio. You know, it was always turning itself down to 0.
Yes, that happens sometimes.
So
it wasn't that.
It was terrible. Like today, I was listening to yesterday's discussion, and I can barely hear myself. So I looked at my computer, and it's like on 5%, or some very, very small number. The microphone is just barely functioning. So I said, okay, enough is enough. I'm going to figure out what's causing this issue, and I scientifically went through the steps. I said, okay, maybe it's my StreamYard, the software for the for the streaming. And I checked it and looked at it, and I saw, okay, I didn't know, and also the potential was discord. So when I turned both of them off, I could see that there's no issue, that the laptop microphone stays at 100%. But as I turned them on, the microphone went down, immediately started going down. So I separated variables. I tried separately StreamYard and then separately Discord, and finally I was able to figure everything out, and now it's not going down. It's at 100% the whole time. Finally, after...
So what was going on?
What? What?
What was the issue?
The issue
What
was
the issue?
there were two issues. StreamYard, both have audio improvements. They both have to,
I'll switch to computer.
What? I can't hear you. Wait, did you just hang up? You just went in and out? Your mic is off. Anyway, okay, your mic is on. Anyway, the problem was that in StreamYard, it has like these audio improvements. And they basically all just reduce the microphone. All the improvements, all they do is they reduce the microphone. That's it. There's like 4 checkboxes and a microphone level. All they do, they just reduce reduce my microphone. That's all they do, nothing else. So I removed all the checkboxes, and then the same for Discord. In Discord, there's a bunch of checkboxes that you can uncheck, and all the audio improvements, they just reduce your microphone. That's it. All that they do is they just reduce the microphone. So I turned everything off, and now my microphone is normal. Yeah, it's unbelievable. I spent so many hours trying to figure this out. Anyway, so you're saying that Dirac believed in the ether?
Yeah, more or less.
Okay.
Basically, yeah.
Okay.
Yeah,
do you?
idea that's basically equivalent.
I don't know what you're saying. What?
I'll send you the link.
Okay, you'll send me a link. Okay. Anyway, do you want to continue discussing Planck's UV catastrophe? Because I found a good lecture. Can you hear me?
Maybe later. No, I want to discuss your rubber ducky.
You want to discuss my rubber ducky? That's terrific. That's actually the most important thing. Okay, so let me just see. So the Dirac sea is a theoretical model of the electron vacuum as an infinite sea of electrons with negative energy, now called positrons. It was first postulated, that doesn't sound like the ether. It was first postulated by the British physicist Paul Dirac. He was British in 1930 to explain the anomalous negative energy quantum states predicted by the relativistically correct Dirac equation for electrons. I have no idea what that means. I don't see how that's relevant to what I'm saying. Why do you think that's relevant to the ether?
It's interesting. It's just that he basically considers that there is a sea of particles that's technically the vacuum.
What? I have no idea what you just said, except for technically the
Basically, I
vacuum.
mean, it basically says the vacuum is filled with all of this.
Maybe you should speak slower today because I can barely understand what you're saying. I'm dying here. I'm trying. I cannot press
Okay.
my headset into my head anymore. Maybe I'll raise the volume.
But but
Let-
are you still not listening to me? Because now I changed to the computer. It should be fine.
okay, okay. No, it's not. I can barely understand what you're saying.
Oh, that's strange.
I think. Let me see on. Let me hear you on my phone. It's not. I can barely understand what you're saying.
Oh, that's strange.
I think. I mean, your audio is very low, so I have to. I'm going to increase your audio to maximum. Not maximum. Right now it's at 50%. Let me see. Can you hear me?
Put on max. Yes.
Um.
Okay. The computer is really close to me, and it's 100%. So it should work.
Yeah. Okay. It's a little better. Okay.
Alright.
So what do you want to discuss? You want to discuss? You want to discuss the paper?
Yeah. I want to. Have you considered putting detectors of all in other positions? Because it of quote unquote relativistic effects. At least it will satisfy the Lorentz transform.
Okay.
Some of
So now your connection is bad.
different.
You're breaking up, and I'm missing most of the words.
Oh,
Yeah.
wow. Yeah, this is not the best conditions.
Yeah.
Like it's okay to work, but it's pretty bad.
Yeah. I don't know what
I
you're.
think that almost everyone I work with is on vacation, so it's fine.
Almost everyone you're working with is on vacation.
Yeah,
How is that relevant? What?
because I don't need to call them.
Because what? You don't have any problems?
I don't need to call them.
You don't need to call them? Okay.
Yeah, I don't need to call them with this shitty internet.
Oh, okay. Okay. So maybe you can just speak slower and try asking again the
I will
question?
try.
Yeah.
Speak very slowly.
Okay.
Okay, so you tried to have you done the thought experiment?
No. What
Putting
have I
more,
tried? Have I tried what doing a thought experiment? Okay.
yes, putting more more reflectors for the clock.
More reflectors by the clock? Why would you? I mean,
For the
I'm
clock
by the clock.
in
What?
different positions.
No.
Like I will draw it. Wait,
You will draw it. Okay.
yeah.
But the short answer is no. The short answer is no because this paper I want to concentrate on exactly one tiny issue. I just want to prove Einstein's second postulate. Let's create a new one. So this is going to be.
Yeah, I'm creating a new one already.
You created a new one?
Creating a new one. Okay. Yeah.
Okay.
So
Okay, I see it. Okay.
More.
You're not drawing anything, right?
Yeah, not yet.
Mm-hmm.
Alright, so you've got the first. This is the part that transmits the wave, and this is the reflector.
Okay.
So the wave goes from here to here. Wait, that's
Mm-hmm.
Using the mouse pad to do this is not the best.
Yeah. Mm-hmm.
So if you try it, for example, the idea of putting 1 year, another year,
What for?
and for example another year, because it will change as you move, right? Like these ones should not be like this. They should be more like more like wait a minute. This is not drawing. I do not know why I'm not drawing. Right.
Mm.
Okay, but they should be diagonal, just so they reflect, to the top one.
But
But you see the idea. So because this is interesting, because if you like imagine the distance from this to this, it would be now this is like really bad, but imagine this distance would be the same as this distance, right? When this is not moving, it will be different from when it's moving in terms of the response to this clock.
what? I don't know what you're trying to say. I have no idea. But
Okay,
but
I will draw again. Okay, so
but
we got this.
what's the purpose? Why? I
Let's
mean,
put one up.
I'm just trying to prove Einstein's second postulate. That's I don't want to do anything else right now.
Mm, yeah, yeah, but this this changes things a little bit. Imagine this is moving this way. The waves here between this one and this one will in this case they will arrive earlier than this.
What? I don't understand what you're trying to do. I mean, why you seem to have you added two more red lines. I mean, I'm assuming what two like another clock
Yeah.
that goes. So you're saying we should have two clocks running simultaneously?
Yes, and when you move the medium, like what happens? Like that's what I'm trying to think about. Because when you move the medium here, or when you move in relation to the medium, this this will be you will have three situations here, right? You have
What?
and this. You'll have three situations here. You'll have one, two, and three. I should put the three on this. You'll have these three situations. Like which ones will be faster?
Well, this is basically an
Like this
interferometer.
one. Yeah, it's basically that.
An interferometer.
Yeah,
An interferometer
basically that.
compares an interferometer compares vertical to horizontal speeds, velocities, basically. But
Yeah, this is basically an interferometer.
I don't see the purpose of. I mean, right? I just want to be able to prove.
The idea is that yes, the idea is that all these are moving at the same speed. It's just that the angles change.
It's not the. It shouldn't make a difference because there is no time. The point is that time is
But it
measured.
will. That's what I'm thinking about. Will it make a difference?
I don't know what you're saying. What? Just speak slower. Speak very slow.
I'm thinking if it will make a difference or not. I'm thinking if it will make a difference or not.
No, nothing can make a
Like,
difference.
for example, this
You don't need to think about it. Nothing can ever impact. Nothing can ever have an impact. This is a clock. However the clock works, that's the definition of time. If it slows down or speeds up, it doesn't mean anything. It can speed up and slow down to an outside observer, but not to the duck. The rubber ducky, that is its internal clock. That is its internal brain. So that is the ticking.
Yes, it is not capable. It's not capable of measuring anything else.
Exactly.
So,
It's the same distances as before and the same ticking as always. Therefore, it's always going to measure the exact same velocity of the waves. And that is all that Einstein said. Einstein just said something that is definitional. His second postulate is definitional. It comes out of the very definition. Once your clock works on the same waves that you're trying to measure. And that just happens to be the case with light, that all particles move at the speed of light. So now we know. At the time of Einstein, they probably couldn't have known this. This is way before, they had no idea. But now we know. Or maybe
yeah, but that's like almost tautological.
it's tautological, but also I would say if this
That's
this
tautological.
it's not just, I wouldn't say it's tautological. I would say if you assume an ether, if Einstein would have assumed the ether, he would have gotten, if he would have assumed an ether. See, he had to first come up with gravity. So once you come up with a gravitational field that is the ether, then, I mean, the ether, the way they imagined the ether in 1905 was, as the name suggests, it's ethereal. It's like less than a gas. It's almost virtual. It's almost not there. They didn't conceive of it as being a firm fluid, a almost a solid. Wait, what happened? Can you hear me? What? You moved away from your laptop, so what?
My internet went down.
I
I went to check the internet. Yeah.
Oh, okay.
Okay, is it better now? Probably.
Is it
Alright,
better now?
the thing is, if you
I know it's terrible. I can barely understand what you're
yes,
saying. Just I'm dying here with my headset. Maybe it's my headset. Every time I get a new headset, you know what? Let me switch to the old headset. Maybe it's the headset that's driving me insane. I don't know.
this shouldn't affect the volume
Okay.
of the microphone. Like it could have like latency and stuff, but affecting the volume would be weird.
Switched. Let me see. Audio. Okay, everything is plugged. Can you hear me? 1, 2, 3. Can you hear? Oh wait. Let me leave the room and come back. Yeah, I need to leave the room. Let me leave the room and come back. Can you hear me? 1, 2, 3. No, audio is no good. Let me try this again. Let me try this again. 1, 2, 3. 1, 2, 3.
So
No.
works like that.
cannot hear myself. Let me try this again. 1, 2, 3. Let me unplug. One, two, three. 1, 2, 1, 2. 1, 2, 3. 1, 2, 3. Okay, this is okay. 1, 2, 1, 2, 1, 2, 1, 2. No. 1, 1, 2, 3. 1, 2, 3. 1, 2, 3. Let me see. 1, 2, 2. 1, 2. What else can I do? Let me see this. Oh, it dropped. Microphone. 1, 2, 3. 1, 2, 3. Okay, now it's not dropping, but I don't know what else to do. Maybe refresh this. One, two, three, 1, 2, 3, 1, 2, 3. Okay. Yeah, it's a little better. I can hear you a little. Okay. It's a little better. We're doing a little better. I can hear you a little better. Let me add Discord again. Can you hear me? 1, 2, 3. Can you hear me? Senas? Can you hear me? Senas, can you hear me? Can you hear me? Before I could hear you, just a second ago I was able to hear you. 1, 2, 1, 2, 1, 2. Can you hear me? Can you hear me, Senas?
Can you hear me?
Yes, I can hear you. I could hear you before. I can hear you. Can you hear me? I can hear you.
But I can only hear you on my stream, on your stream. Wait a minute.
So leave leave the room and come back. 1, 2, 3, 1, 2, 3. Try. Can you hear me better now?
Yeah, just fine.
Okay. Let me
Okay, fine.
let me see about.
The idea was,
Mm-hmm.
let's see, my idea was to make the calculation to see if to see what would happen if you start putting different clocks in different parts. Start putting different reflectors in different parts.
It's not gonna make a difference. It can never make a difference. That's the whole point. That's my thesis.
Yes, but we need to prove that.
But that is, yeah, that's my paper. So, but my paper is like, it doesn't matter as long as the distance stays the same, which it must, because the duck is not changing, the duck is not stretching or bending. So the duck is hard. The duck is made out of
It should be the same.
By the way, I can hear you much. I can hear you much. I can hear you much better now. I mean, it's like night and day.
Okay, great.
Yeah, I was losing my mind.
No, but it should be the same. Yes. If you think like, if you think I can hear myself now. If you think about like circumferences, it will be the same.
What do you mean you can hear yourself?
It will just like the two-way will be the same, right?
What do you mean you can hear yourself?
Oh, I can hear the echo.
Really? Let me see. Let me test
Yeah,
it on
but
the
it's
stream.
not a problem. But let's just see in the stream if there's a problem there.
No, no, no. Until we finally figured everything out. Let me just let me hear if this is a problem on the stream. No, no, no. Until we finally. There's no echo.
Okay,
Let
so
me just let me hear if this. There's no
so yeah,
echo. So you're hearing it from two sources. You have two sources open. You left maybe the YouTube open.
no. I only have one source.
Hmm.
But it's whatever.
Um. Yeah, it might be that Discord, but I'm wearing a headset. So how can you be hearing
Yeah, it's weird.
like
But
my
I can definitely hear myself. Maybe you have the stream going or something.
no,
But it should be more delay if it was the stream, so no, it's not that.
I don't have yeah. Well,
No, it's not that.
it's only you
No,
because
but like you see, the idea would be proving like if none of these move and they're all at the same distance, that it will not matter how the medium moves. That
exactly.
would be the point.
Exactly.
The two-way, but you have to say like, but we have to prove that the two-way speed is the same because the one-way speed is not going to be the same, right?
What do you
But
mean
the
one
two-way
way, two
speed,
way? What do you mean one way, two way?
one way is like one way is like this, and two way is like this, and this. Yeah, see. The point is to prove that the two-way speed of light, which has been a problem for a long time, that the two-way speed of light is the same. That it doesn't matter where you put the detector, as long as it's the same distance, the measured there will be no differences in the measured time.
So you're saying we should have two clocks?
No, it's just to compare.
I can mention it. I'm not gonna add more images, more
No, this is
graph.
important. You should think about this. Like you should think about this problem because this is the part where you make the formal proof. Because if you only have one, it's basically tautological. Like it could not, it could never, you can never measure anything more than your clock rate if you only have one clock. Like that's obvious. But if you can prove it for more different clocks, as long as they are at the same distance, then that's relevant.
Right, I'm saying I can talk about it, but I'm not going to add more figures. The only figures I'm going to use is for one clock, not for the other.
Okay, but think about this. Think about this. Yeah,
No, no, I'm saying
you
I
want something. Yeah.
it's a good idea to add more clocks and more complex clocks in a discussion, but not in the figures. I don't want to have because I have so many figures. I have like almost 20 or 15 figures right now.
Yeah, but you can reduce that for one. You shouldn't have that many figures.
What?
You should reduce that. For one clock, you should not have that many figures.
No, it's okay. It's better to have more too many than too little. I don't want to this needs to be a paper for, I don't want to have any misunderstandings. But you write that I should mention in the notice section, so I'm going to add notice that we can make our clock more complex, such as add a horizontal clock. However, this will not change the measured speed of the waves, because the definition of speed is distance divided by ticks. The distance.
Alright, but anyway, when I have time, I will write this more formally.
Okay, that'd be great. Okay, the distance never the distance never changes as the rubber ducky does not stretch. Does not stretch, and the tick never changes. The tick never changes because the tick never changes. As the metric of time. Okay, that's it. Okay. But I decided this paper should be very, very specific. And I'm not going to mention the ether except for in the, at the end, at the conclusion, just that, if they would have, I want to just, touch the ether. I don't want this to be about the ether. I don't want them to react. I don't want them to think of me as a flat earther. So I don't want this paper to be about ether. Wait, did I lose you? Are you there? 1, 2, 3, can you hear me? I cannot hear you. I can hear noises, but not you. You're doing something, but I don't know. I cannot hear you. Now you're gone. Yeah, this is really amazing. This is the great technology. Can you hear me? 1, 2, 3. No, I cannot hear you. Nothing. I can see you're not talking. Unfortunately, maybe because your connection is unstable, Discord is losing its mind. This is, I heard that technical difficulties can cause.
Yes, I'm having technical difficulties.
But did you know technical difficulties can cause like actual heart attacks? Did you know this?
Yeah, I believe that.
I mean, it can drive you insane.
Yes, I know I know about that better than a lot of people.
What?
Trust me.
I don't know what you just said, except for trust me.
I know about that better than the vast majority of people.
Yeah. I hate, technical difficulties are just terrible.
Yeah.
And I'm traveling, so, but I created this this office for myself that is just barely functional, but it's terrible.
No, yours is fine.
Oh.
You can stream, you can do all of that.
Yeah, but I have this fan that decided to stop reacting to the remote control, so it's always on, and it's killing me. This fan, it's I need to replace it. This is such a nightmare. Anyway, going back to our discussion, so do you want to go over the paper? Do you? Because I'm trying to go over it.
No, I've read the paper. I understood it. Yes, it's not necessary.
Okay.
But we can, we can go more as in like maybe if it's well explained or not, something like that. If you want to do that now, but maybe you haven't finished yet, so.
By the way, my speaker is on 100%, and I'm just barely hearing you. Just be aware of that.
Again with that problem.
Yeah, I mean, my microphone is 100%, but now my speaker is 100%. I can barely understand what you're saying and barely hear you.
Wow. Okay, fine. I don't know what to do about that.
Just, keep close to
I
the
don't have the
mic.
equipment
What?
today. I don't have the equipment today.
Yeah, just try to stay close to the microphone and speak as loud as you can.
Okay, okay.
So,
So do you want to go through the paper a bit or not? Or no?
yes, I definitely want to go. I mean, I just want to go over the paper. I don't want to do anything else because everything else for me right now is a distraction. Like, even quantum mechanics right now is a distraction. We need to get this paper out. I need to put it on archive or something and, start getting reactions.
Okay, let's go over it.
Okay, so
You're gonna show it on the screen?
yeah, I'm sharing it on the stream. I can't share you and it. So people right now cannot hear you.
Okay.
So whatever you say, I'll just repeat. But okay, let me go through the. Okay, well, let's go. So I reduced the title to just proof of Einstein's special relativity's second postulate. So proof and postulate, that's already a contradiction. So that's good. Maybe instead of second, I'll write second literally with a capital S. Proof of Einstein's special relativity's second postulate. Okay, today's the abstract. So I'm gonna start. So in his paper, Albert Einstein, blah blah blah. I never did that. I need to do that. I'll come back to that. Okay, so let's read what I'm saying here. So in this paper, we're going to prove Einstein's special relativity's second postulate. The speed of light is measured by all moving inertial. That's not his postulate. So I'm just gonna say I'm not gonna say anything. Okay, for that we will introduce a thought experiment based on Einstein's, let's capitalize, Einstein's photon clock. Einstein never had a photon clock. Apparently this is not Einstein's thought experiment. Did you know this?
No, I did not know that.
Yeah, I looked it up. It's not because people they say, "Oh, Einstein's thought experiment." Everything is Einstein thought experiment. You actually look up what Einstein said. The guy barely said anything. So it's based on the famous.
Fielding is very weird. Like
One second.
I watched one of your streams, but I watched like not while you were streaming. Well, you were going, or maybe I was there. I don't know. But you were going through a paper of Einstein, and like some of the things were just incorrect that he was talking about. Like it was like very strange to see that. I don't know what to say.
Okay.
Like
Sure.
he referred to the magnetic field, the magnetic field and electrical field, depending on the movement of a magnet, on the relative
Oh
movement of a magnet
no!
and the conductor.
Wait, that's the
But that's
first.
incorrect.
Wait, that's the first paragraph. That's the first postulate.
Yeah,
So you're saying that's
that's
incorrect?
incorrect. Yeah, you do. Do you know the homopolar generator?
The what? Yeah,
The
I mean, no, but
homopolar generator.
the what power generator?
Homopolar.
Homopolar?
Polar. Or,
No.
yeah, one pole.
Oh, unipolar?
It's equivalent linguistically. I will show you.
Okay.
You will see that later because it's very
Okay.
interesting.
Okay, wait, so let me.
Basically, if you rotate a magnet, but if you rotate a magnet and you don't rotate the conductor, there's no electric field. But if you rotate the conductor and But if you rotate both of them, there is electric field. But you'll see later.
Wait, what? Wait, as far as I know, it doesn't
Yes, if you
matter.
rotate both of them, there is an electric field.
What do you mean if you rotate both of them in the same direction?
Yeah,
What?
yes, it's weird. You get eddy currents.
Eddy currents?
Wait.
Let me try. I think we can show the paper here as we're working. I mean, Einstein's paper. Can we open it? No, it doesn't let you open it here. Share your screen. We can share this one. So it's not gonna let me. Oh, it is. Okay, but I can't scroll. Wonderful. Genius. Options. Stop. Show. Show my screen share. Yeah. Are you there?
Yes, I was looking for a video on your monopolar generator.
So wait, this is his first paragraph. So it is known, this is how the paper starts. It is known that Maxwell's electrodynamics is usually understood at the present time when applied to moving bodies leads to asymmetries which do not appear to be inherent in the phenomena. Take for example the reciprocal electrodynamic action of a magnet and a conductor. The observable phenomenon here depends only on the relative motion of the conductor and the magnet, whereas the customary view draws
Yes, that's not entirely correct.
Wait, let me just try to understand what he's saying.
It's the movement.
Let me just finish. Whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. For if the magnet is in motion and the conductor at rest, there arises in the neighborhood of the magnet an electric field with a certain definite energy. So this is if the magnet is in motion, the conductor at rest, producing a current at the places where parts of the conductor are situated. But if the magnet is stationary and the conductor in motion, no electric field arises in the neighborhood of the magnet. Is this true?
Right, but if the magnet is stationary and the conductor is in motion, no electric field arises in the neighborhood of the magnet. In the conductor, however, we will find an
electromotive force to which in itself there is no corresponding energy, but which gives rise, assuming equality of relative motion in the two cases discussed, to electric currents of the same path and intensity as those produced by the electric forces in the form. I have no idea what he's saying here. I don't even know what reality. I don't know what reality is. I don't know what Maxwell says, and I don't know what he's saying. So first tell me what reality is. As far as I know, it doesn't matter what you move. Either you move a wire through a magnet or a magnet through the wire, you get exactly this.
But it matters. But
what do you mean?
It's not all the same thing.
Wait, hold on. So,
But he's actually saying that.
hold on, wait. I don't care what he's saying.
Uh,
Let's start. There's three things I don't know, so I need to go step by step because I haven't done electricity in 100 years or so. So, first, what is reality? So, if I take a magnet and a wire, then if I move the magnet next to the wire, I'll get voltage. And if I move the wire next to the magnet, I'll get a voltage, right? It doesn't matter as long as they move relative to each other, we'll get voltage in the wire, right?
no, that's not entirely right, actually. So
Let's can we watch
the
can we
magnetic field doesn't move. The
go ahead.
magnetic field doesn't move exactly like that with a magnet. It depends on what kind of motion.
Okay,
So
let me pull up a video, a YouTube video.
you have to move the magnetic field. That's the key. And it depends on which, what is moving the field. And yeah, as Einstein says there, the effect in one case appears around the magnet, and in the other case appears in the conductor. However, electricity is generated either way. A
Um,
little bit different.
I'm confused. Okay. Let me pull up a video, an
I have to
experiment.
study this better. Anyways,
You have to study it better.
yes, I have to study this a little bit better
Let's
because he's
look.
making some interesting claims.
Okay, let's look up an experiment magnet and wire. I'm sure somebody did the experiment.
Yes, that's the typical one, but that's not detailed enough.
MIT physics demo jumping wire.
Okay, you're not sharing that.
No, I'm not yet, because once I do, they're not gonna hear you. Okay, let's. I don't even know how to share, because now I have two shares. I don't know which one to share. I'm sharing something in something. So let me switch. Yeah, it's gonna be impossible. So let's stop. I'm gonna stop. It's too confusing. Let me stop this share. How do you stop this share? This share I'm gonna stop. Okay. That's fine. Now I will go and share this YouTube video. Alright, so you should see it on the stream. But there's no talking, so I don't care. This is moving the wire next to the magnet. I don't know what that is. No one is talking.
It's so good. Element is formulated for anyone on a mission to restore health.
No talking.
Today on Sci Guys, the simplest electric train. Today on Sci Guys, the simplest electric train.
Simplest electric, magneto electric. Okay. Yeah. Okay. Nothing, no talking. Where's the audio? What happened?
Hi, so I'm quite sure a lot of people know what this is. It's a synchronous motor. It's a turntable motor, actually, from a microwave.
Okay, I don't care. No talking.
Why does this happen? Well, copper is not magnetic.
I don't care. Don't care. No talking. No talking. No talking.
Patent for this came about in 2012.
I don't care. Don't care.
Axis, how likely you are.
I need an experiment. No talking.
I made a video about a
I don't care.
Hey guys, welcome back. I'm Nate with the King of Random, and today we're going to be doing a few small projects that let us take a look at the relationship between magnets and electricity. Growing up, I always loved playing with magnets, and over the years, the quality of magnets available has...
I want a simple experiment.
Alright, the second activity that we did today was making an electromagnet. So what I have is a piece of... Alright, the second activity that we did today was making an electromagnet. So what I have is a piece of wire. It's copper wire that's covered in a protective coating. I have an iron nail, and I have a battery. And here in just a bit I'll have some paper clips also, but this is the main thing that it has. So we're going to read the directions and go through each individual part. Very first thing it says to do, leaving a 2 to 3 inch tail of wire at the beginning, so about as long as my thumb, so about this long. Wrap your wire around the nail as many times as you like. So I'm going to go 12 times. I think that's a nice round number, so I'm just going to go 1, 2, okay. So 12 times around the nail.
I'm skipping.
Not overlapping, but it is covering most of the nail right here. Here's my lovely diagram. That is my wire wrap nail. You can see it. Carefully hold one end of your wire to the positive side of your battery to try and pick up as many paper clips as you can. Battery. I'm going to put this in. I'm just going to hold it on here. You can do this with a holder as well, but this is just easier for me. And I'm going to make sure that my metal is touching metal and I'm holding it onto the battery. Okay, so here's my magnet. And I'm going to use that and pick up as many paper clips as I can. Clip on, but it's not quite strong enough to actually hold. No, oh, there we go. Right on there.
So what she's saying is you can turn electricity into a magnet, but that's not what we want. We want two things moving relative to each other. It's a different experiment. This experiment is irrelevant. I see you're still there, but you're not talking. Okay, let's keep looking. No one is talking. No one is talking.
Hey everyone, today I'm going to be showing...
Don't care. Don't care. Don't care. No talking. People, my God. How to make an electromagnet. That's the same issue. We're gonna need to find two different experiments. One is gonna be moving a magnet. We need to just move a magnet. Move a magnet next to a wire. So current carrying wire. Where's the magnet? There is a battery. I don't want there to be a battery. So if there is a battery, it's useless.
I'm now going to sprinkle some iron filings onto the plastic.
This is just a magnetic field around a wire. I don't care. Again, carrying current. I don't want there to be current.
Scientists have discovered a conductor moving in a magnetic field causes free electrons in the conductor to be.
Okay, if we're not going to watch an experiment, at least let's watch an animation.
A conductor moving in a magnetic field causes free electrons in the conductor to be deflected at right angles to the magnetic field. If we stop moving the conductor, electrons are no longer deflected. But as the conductor again cuts through lines of magnetic force, electrons in the wire are deflected.
That's as far as I know. It doesn't matter who's moving relative to whom. Either the wire cuts through the magnetic field or the magnetic field cuts through the wire. How is this? This is what Maxwell predicted. This is the Maxwell either fourth or third equation. What is Einstein saying? I don't know what he's saying. I have no idea what he's saying. I don't know what he's talking about. What is the first postulate?
These deflections establish a negative and a positive charge at the ends of the conductor. In effect, there are two charged terminals, just as in the wet cell, capable of producing a continuous flow of electric current as long as the conductor is moving. An electric current can be generated quite easily. Simply move a wire conductor through a magnetic field. See what happens? As the wire passes through the field, the mirror indicates a small current is being produced.
That's it. That's all. Let's see if they do the reverse.
It was Michael Faraday who discovered this first.
Yeah, this is the Faraday's law.
Great experimentalists of all times. He found the relationship between a magnetic field and the electric current it causes.
This is, let me see. Yeah. This is dB dt. This is a change in magnetic field. and it causes, what does it cause? It causes, I think it's del cross E. I think it's del cross E equals the negative dB dt or something.
In 1831, Faraday said a magnetic field produces an electric current and voltage in a conductor.
Let me slow this down.
When the conductor cuts through...
When did he say this?
In 1831.
1831, this is before, everything for me is before and after the Civil War. Okay, this is before the Civil War.
Faraday said a magnetic field produces an electric current and voltage in a conductor.
Magnetic field induces, well, it's a changing magnetic field induces.
When the conductor cuts through magnetic...
Okay, so that's a changing magnetic field as far as the conductor is concerned.
Lines of flux.
Right, these are the lines of flux.
Current and voltage generated in this manner are called induced current and induced voltage.
It's like, why would the magnet care if it's moving or if the wire is moving? Why would I care? Why would anybody care? The question is, how is it working internally? What is causing this? I mean, this has to do with the rotation of the electrons inside the ferromagnet.
Relationship is called Faraday's law of induction.
Good. So the only video we have is of an animation. What else is new on the internet?
I'll send you 2 videos. One is a bit more detailed.
Oh, the best thing is if you send me videos, because if you send me videos, I can click them here and we can watch them here. That's the best. Yeah, I forgot. That's the best way to share.
Right.
Yeah, because this way you can talk and we can
but
hear
I'm
you.
sharing on the general chat, but I'll share you.
No, it's okay. I mean, I'm gonna click the link. You'll be able to. Oh, you're not gonna see. You're gonna have to listen to it on the stream. Yeah, everybody else will see it, but except for you. Yeah. Okay, let's hear it.
Bad presentation. It just totally confused you. In mode 0, where nothing is moving, both classical and new electromagnetism, they both predict there'll be no voltage measured at the voltmeter. In mode 1, where only the disk is spun, both classical and new electromagnetism both pretty much come up with...
Wait a minute, this guy is, he's like me.
Yeah, you can see your stepped up, yeah.
Oh, that's Destiny. No, I don't want to watch Destiny. I want to see only, known...
See the previous one then.
Yeah, okay.
Hello, welcome to Forest Learn. In this video, we'll be discussing an
explain.
What?
Yeah, that one.
Okay.
Example of electromagnetic induction, known as the Faraday disk dynamo. This is
Explains
named
why
after
different ways of generating electricity.
Okay.
Michael Faraday, one of the
Without
pioneers
theoretically distinct.
Without theoretical distinct?
That are theoretically distinct.
That are theoretically distinct?
Yes.
I don't understand. What do you mean theoretically distinct? Distinct from what?
From each other.
Oh, he's going to show multiple ways? Okay.
electromagnetic induction. The Faraday disk dynamo is an example of an electrical generator.
Okay, let's think about this. So this is current. So current is being induced. Let's see what he says. So something is rotating. So the Faraday disk dynamo explained. Okay.
Generate electricity via induction. Generators are a massive part of the induction topic, and the Faraday disk dynamo quite often turns up in exam questions to do with electromagnetic braking systems of vehicles. So it's well...
Electromagnetic braking systems of vehicles? What? What vehicles use electromagnetic braking? Unless these are electric, like an electric car does that. Fine, okay. It's not a braking system. It's just the built-in dynamo. When you let go of the gas, it refills the battery from, from the inertia. It slows you down and refills the battery, okay.
Your time to understand the physics behind the Faraday disk dynamo. This video is part of a series of playlist of videos on induction. In our intro to induction, I explained how I've broken the topic down into 3 different types of induction to help you organize your understanding of this challenging topic.
Okay, 3 different types of electromagnetic induction. Type 1, cutting field lines. That's good. Type 2, flux changes in a loop. Okay, but that's still very similar, because as you're moving in and out, these lines are moving back and forth. You're cutting through. It's very similar to this. And type 3, overlap of type 1 and type 2. I don't know what he's showing here.
Previous 2 videos dealt with the first type, cutting field lines, where we discussed Faraday's and Lenz's laws, when a wire cuts across magnetic field lines. The Faraday disk dynamo is an example of this first type, and the discussion assumes you have some familiarity with Faraday's and Lenz's laws. To get the most out of this video, I strongly encourage you to watch the previous 2 videos first.
Yeah, we need to go watch the previous video, not this one.
Once you've watched the video, why not try to explain what you learned to a friend or a family member, as a test to see how well you understood the material. The Faraday disk dynamo consists of a conducting disk, which is shown in pink, which is placed in a uniform magnetic field. The disk lies in a horizontal plane, and the magnetic field lines, which are shown in black, are directed vertically up. It may appear as though there aren't any magnetic field lines poking the disk in the southern and eastern regions of the disk, but I haven't drawn those field lines in on purpose, so as not to overcomplicate the diagrams later on in the video. So you'll just have to imagine that there really are magnetic field lines poking through this disk uniformly all over the disk. The rod shown going through the center of the disk is also a conductor, known as the shaft.
Okay, we need the previous video. Let me go. Can you get me the previous video?
No, I don't know. I haven't seen it.
Because he says the previous video is where he discusses this. But look, I don't see, this doesn't make any sense. What Einstein says makes no sense. I just, I don't know what he's talking about. What is his point? Share.
He probably makes the point later.
No, he doesn't. This is just a postulate. It is known. This is how he begins. You know what? Let's take this. Let's take this to ChatGPT. Let's see what ChatGPT says about this. Forget it. I'm not gonna share. It's too difficult to share because I'm sharing twice and I never know which one I'm sharing. So I'm just gonna punch this in. See what they say. Okay, you're touching upon a critical insight that contributed to the development of Einstein's theory of special relativity. This observation highlights the inconsistencies in classical understanding of electromagnetism as described by Maxwell's equations when applied to moving bodies. Really. Here's a breakdown of the situation you described. Maxwell's equations, the classical electrodynamics. Maxwell's equations describe how electric and magnetic fields interact and propagate. In the classical view, these equations suggest that the electromagnetic fields depend on the absolute motion of the sources, like magnets and conductors, rather than their relative motion. Why would you say that? What? That never shows up in the equations. What are you talking about? The equations are just a summary of experiments. The equations come out of experiments. And no experiment has anything to do with anything being absolute. This is ridiculous.
Yeah, he's talking about moving in relation to the field.
Moving in relation to the fields? What?
Yeah, I think that's what he's talking about.
What he's saying here is nonsense. I cannot fathom what he's saying here. If you, the equations come out of experiments. No experiment. How can you say that there's a problem with an experiment? I just don't understand what he's talking about.
But the equations work in the other way as well.
The equations work in the other way?
Yeah, they work with both relative and absolute motion.
Wait, you know what? Why don't you join me on
It
this?
doesn't even matter.
No, listen. I'm
For
gonna give you the link. Join me in StreamYard. This way everyone will hear you. I don't have to go back and forth. Here's the link. The link is on the stream. Click the stream. You'll enter into the backstage. I'll let you into the stream. This way everyone will hear you. I don't have to run back and forth like a nutcase, which I'm not.
okay, so I leave Discord.
Yeah, you leave. You don't. It doesn't matter. You can stay or leave. It doesn't matter. But you can, if you enter.
Yeah.
You should leave Discord after you enter the stream. So you can tell me what you're doing, and and when you tell me that you're in the backstage, I'll let you in. Okay, meanwhile, I will continue trying to make sense of this guy. So, magnet in motion. Okay, asymmetry in classical theory. The asymmetry arises when considering the interaction between a magnet and a conductor. Magnet in motion, conductor in motion, conductor at rest. Okay, when the magnet moves relative, are you able to make it in?
Yeah, just I know how it is, but it's very slow. Like my internet is just very slow.
It doesn't matter, but I want you to be able to talk and for people to hear you. Otherwise, I have
Yeah,
to.
I know, but it's taking long to load things.
Okay. That's okay. So keep waiting because it's worth it. I think it's worth it. Otherwise, maybe because it's gonna stream. You're gonna get the stream and then it's gonna upload. We'll see. Okay, let's test it. It's worth testing. Maybe it will be better.
Yeah.
Okay, so I'm gonna continue reading. So when the magnet moves relative to the stationary conductor, so this is the magnet moving, a changing magnetic field. Let me just get a sip of water. A changing magnetic field is observed in the vicinity of the conductor. That's interesting. I mean, that's kind of obvious. This changing field okay. This changing field induces an electric field generating a current within the conductor. The classical explanation attributes this current to the presence of an electric field with specific energy. So the classical explanation is that the magnet moved and created an electric field, and the electric field induced an electric effect on the conductor. The changing field induces that. Oh, that's interesting. But what is the difference? Symmetry in observations. Empirically, the effects observed are symmetric. The outcome depends only on the relative motion between the magnet and the conductor. Whether the magnet or the conductor moves, the result is the same. A current is induced. The classical distinction between these cases was problematic because it suggested that the electromagnetic effects depended on the absolute motion of the bodies, not just their relative motion. Wow. Oh my god. Oh my god. This is incredible. So there's no difference in the observation, but there is. Okay, so this is incredible, but the equations. But who cares about the equations? The question is, I mean, everything arises from observations. It's not like somebody predicted these equations. These equations are just summaries of observations. Implications.
Yeah, but Einstein says it's slightly different.
I don't care what
In the
Einstein.
paper.
I mean, ChatGPT is already saying something that they're different. ChatGPT says they're different. But the question is, how could they be different? It's based on experiments. The Maxwell's equations are summaries of experiments. How could you these are not predictions. These are just summaries of experiments. This is, we did a test. This is what we noticed. Here it is. When we write it in mathematical form, the mathematics is just a shorthand for a story. So what's there cannot be an issue from the mathematics in this case. This is not a case where there's no predictive power from these equations. The only predictive power is the electromagnetic wave, and the speed of the electromagnetic wave. That is what comes out of that's the prediction that comes out. So I don't know. Implications for relativity. These asymmetries pointed to deeper issues with classical physics, suggesting the need for a new framework. Einstein's theory of special relativity addressed these inconsistencies by postulating. No one teaches the theory of relativity from this point of view, from this experiment. They just teach it from the observation that the speed of light is a constant. No one discusses this asymmetry. I've never heard this asymmetry being discussed anywhere. Oh, I hear you entering. Okay.
Okay, I entered.
Okay, so you can leave. You can leave Discord. So from now on, everyone will hopefully hear you. There should be no reason they wouldn't hear you. So they're going to hear you.
Okay, so
yeah,
I can be out.
Let me just do this. Okay. Alright, so no one ever discusses these asymmetries. Einstein's theory of special relativity addressed these inconsistencies by postulating that the laws of physics are the same in all inertial frames, and that the speed of light is constant. Now the speed of light it comes out of Maxwell. So he doesn't need a separate postulate. The fact that, I mean, all you need is the second postulate. You don't need the first postulate. Anyway, so he says, Einstein's theory of special...
you need it for acceleration.
But we're not dealing with acceleration. Einstein's theory of relativity of special... For inertial frames?
So no forces are there.
What? What? What did you say?
Yeah, I think that's what it means. Like inertial
I didn't hear
frames.
what you said. I don't know what you said. Repeat what you said. I don't know what you said.
Yeah, it talks about inertial frames. Like, I'm trying to remember what that is.
An inertial frame? That just means it's constant speed relative to each other. Two frames.
Oh yeah. So there's no acceleration or force.
Yeah. No gravity, no acceleration. Yeah, just what do you call it? It's called not homogeneous motion. Whatever. It's constant speed, constant velocity. It has a name. When the lectures of special relativity, they always use this name. Why is this phone not shutting down? Okay, 97%. That's not good. Okay. And this one, 73%. Okay. Are you playing ping pong? Okay, yeah, I'm hearing ticking. Anyway, oh, maybe it's the noise that I was making. Okay, Einstein's theory of special relativity addressed these inconsistencies by postulating that the laws of physics are the same in all inertial frames, and that the speed of light. So the way that like Lenny Susskind explained it is the law of juggling. The classical physics is just he says in order to juggle, there are certain laws to juggling. So that is, he said you can think of the classical physics, just think of the laws of juggling. So the laws of juggling don't care if you're moving in a moving train or in a non-moving train. That's what, but this is different. Einstein's theory of special relativity addressed these inconsistencies by postulating that, this is the postulate, that the laws of physics are the same in all inertial frames, and that the speed of light is constant. Now the speed of light is now it's a different essence, because the speed of light it comes out of Maxwell's equations, regardless of the observer's state of motion. This led to a reformulation of electromagnetism, eliminating the asymmetries and establishing that only relative motion matters. But that's nonsense. The reason only relative motion matters is because our internal clocks run on Maxwell's equations. That's the only that's it. We are all, our brains, our reality is Maxwell's equations. So we can never step out of Maxwell's equation, except for with an interferometer. The only way we can tell is with an interferometer. And even then, Einstein explains it with GR. So even that's useless at this point. But he's wrong. I don't know what else to say. What?
It's also for inertial frames, but
I don't wait. I don't know what you're saying. Start over.
It's also for inertial frames.
It's what? It's also for inertial frames?
Like
oh, it's just for...
Yes, if there's acceleration, it doesn't work.
How do you know that?
Well, it doesn't.
Wait, how do you know?
Like, even the postulate doesn't include that.
No, but how do you know that that something changes during acceleration?
Okay, in your case of the rubber ducky, it won't change anything.
Right. So my conclusion, when we get to his next paper, General GR, I think his equivalence principle is incorrect. And I looked it up. No one, as far as I'm concerned, no one has ever tested that during acceleration you have time dilation. They say that in particle accelerators they measured it. I doubt it. I want to see the raw data. I don't believe it. That's a contradiction. That would be a contradiction to the theory of ether. But in GR field equations, I never saw acceleration. Acceleration doesn't cause anything. Acceleration doesn't bend space and time. Acceleration doesn't bend space and time. That's nonsense. In Einstein's field equations, there's no term for acceleration doesn't show up. So it's nonsense. His equivalence principle is complete nonsense.
Yes, it's a little bit strange, especially if you think if the like it's supposed to be that gravity is equivalent to the whole system being accelerating, and we can distinguish one thing from another.
What? No, you gotta speak louder. I don't know what to do. You gotta speak louder and clearer
Okay,
and
so
slower.
the postulate is that gravity is equivalent to just non-changing acceleration, basically, in the opposite direction.
Wait, in this paper or in the next paper?
No, in the principle of equivalence.
The principle of equivalence in the GR paper?
I don't know if it's there or not, but I'm talking in general.
So in GR, I didn't get to GR yet, but the way people teach GR, everybody teaches his equivalence principle. And
Yeah, I know what it is.
So it's wrong. And there's no, as far as, we'll get to it. I don't want to discuss it. I don't want to.
It may be wrong because if light moves with the ether, it will be wrong.
Exactly. Yeah. I'm sure, like, my intuition is very strong. It's wrong. It's absolutely wrong. And I don't even see how it's relevant for his GR, for his equations. I don't see. I mean, I didn't do the course yet. I did like the first 3-4 lectures, that's all. Anyway, getting back to this. So the only reason, so I'm not sure what his problem was. I'm not sure what the problem was, but it gets fixed just with the rubber ducky. The rubber ducky fixes everything. Because the rubber ducky says that we are Maxwell's equations. That's why it doesn't matter. That's why it's all relative. And that's why we always measure the speed of light to be a constant, because we are Maxwell. Our brain is Maxwell. Our brain is light. Everything in the universe is light. So anyway, let's get back to, okay, at least now we know. Let me just finish reading ChatGPT. Einstein's insights allowed for a more consistent and symmetrical formulation of physics, where the electromagnetic phenomena depend solely on the relative motion between objects, leading to the groundbreaking development of the theory of relativity. There's nothing groundbreaking about it. It's just a rubber ducky. Okay, let's get back to the rubber ducky proof. Okay. So in this paper, we're going to prove Einstein's special relativity's second postulate. So before we do that, we need to explain why this is groundbreaking. So he assumed it out of thin air. So Einstein assumed it out of thin air. I mean, I don't know how else to say it. And we can quote, I like the quote from Shankar. As Professor Shankar says, we'll put a quote, the universe has conspired. This is Einstein's postulate, that the universe has conspired to hide your uniform motion. This is Einstein. Shankar spends half an hour. This is Yale. Shankar spends half an hour explaining this. I mean, I don't want to say it's magical, but it's as close as possible. This is anyone who teaches special relativity explains how the universe is weird. Does ChatGPT say this? Does he say how the universe is bizarre? You're touching upon a critical insight. It's unintuitive. They say unintuitive. Let me see.
Oh,
Does
okay.
he No, he doesn't say there it is. Counterintuitive. Yeah. Okay. So implications for relativity. The constancy of the speed of light leads to several counterintuitive implications, such as time dilation and length contraction. For example, time appears to pass more slowly for an object moving at high speeds. So that's not as bad. The way ChatGPT says it, it's not as bad as other physicists present it as this magical universe that who's the worst of all? Richard Feynman. He's the very worst.
Yeah, have you seen his video about Richard Feynman explains magnetism? Or rather, he doesn't explain magnetism.
I didn't see, but you're talking about Inductica?
No, maybe, I don't know. I just that there's a funny part where the interviewer asks what is magnetism, asks him to explain what magnetism is, and he just and he starts like getting up from the chair. It's almost like he's going to start a fight.
Yeah, I remember. Yeah.
Yeah, he gets really pissed off at that question. Because I mean, he can't explain it in reality.
Okay, but can we explain it? Can you explain it?
I have some hypotheses, but I would have to confirm them. What I think that magnetism is some kind of stable movement, like of some kind of stable rotational movement that interacts with other types of the same stable rotational movement. Because if you, for example, if you put like imagine like a cylinder, if you put it rotating in the water, and then you put a cylinder rotating in the same direction near it, they let's say one of the faces is facing one of the faces of cylinder one is facing the back of cylinder two, and they're rotating counterclockwise when seen from.
Wait, I'm lost. You completely.
Yes, it's probably better to draw it.
Yeah, okay.
But like, imagine two cylinders rotating in the same direction, one on top of each other.
Wait, well, what do you? So wait, what are you trying to explain? Magnetism?
Yeah. Imagine that.
But
two cylinders,
Einstein.
one cylinder on top of each other, right? On top of another.
1 second. Hey, Hamburger. What's up? How are you?
I'm good. Are you live right now?
Yeah, we're live. Do you want to talk?
You're echoing really bad.
Yeah, that's what I've been told. I turned everything off on Discord. All the features that help, I turned them off because it keeps turning off my microphone. And it destroys all my streams. So I'm sorry.
If you go to where your microphone input is, do you have it set so that it's supposed to be feeding back so that you can hear yourself? Because maybe that's why.
Okay, let me share ChatGPT and
yeah, it should be right underneath where it says mic or something.
Let me see video. I mean, I turned off echo cancellation, but that can't be related. Oh, noise suppression. I guess I didn't turn that off.
You've turned off echo cancellation, then it's that. You have turned it on.
But what?
But that may be why you were getting cut. You were getting your
I'm getting
portable
here.
image.
Share this tab here. Everybody can see my tab. I don't have any private information here. So, voice activity. This is sensitivity. Soundboard. I don't care. Hardware
Echo
acceleration. I don't
cancellation.
care. Echo. But if I tap this, it's gonna reduce my mic. It's gonna right
Yeah,
away kill.
probably.
Yeah, it's already killing my mic. Yeah, it's already killing my mic. So I can't use that.
Yeah, whatever.
Hamburger, I don't know. I cannot use echo cancellation. And that's it. I can't touch it. I cannot
Sorry,
touch
dog.
it. What? So
I said sorry.
yeah. So am I echoing bad?
No, only me.
So okay.
And I can kind of at times like hear stuff in the background,
Let me.
which is like disorienting because it's like not me, you know. And then every once in a while there'll be like a random like voice from your speaker. It's probably just like feedback.
There's no wait. Senas, Senas is with me on the stream. Was I echoing when you were in Discord?
Yes.
We're on Discord.
No, I know. That's so he moved to my stream instead. So yeah, as long as I'm streaming, I cannot get rid of this echo. I guess. I mean, Discord is garbage. They drop my mic as soon as I let them do anything. They immediately bring my microphone to 0, and that's it. That's the end of the stream. It kills all my streams.
Dude, I've been getting kicked from Discord like a lot lately, and they keep telling me servers are down like constantly.
Really? No, I didn't.
Oh, that happened
yeah,
to
since
me
like
as well.
last night, I've been getting like kicked from places while everything is connected, and then it says like loading server check, and I'm just like, what the fuck?
I don't know. I'm using.
Apparently, that can be like regional.
I'm using Discord less and less with every passing day, because I used to love it to go into different rooms to debate, but to stream my debates. But it's basically impossible to stream debate on Discord. Like anywhere you go, they ban you if you stream debates. So it's useless. What is the purpose of Discord if you cannot stream debates? It's like if you're a small channel and you have to come to people to debate, you can't stream it. If you're
Why
a
did
big
they ban
channel,
you?
that's the way Discord is. They don't talk, they ban. Welcome to the 21st century. They don't talk to you, they just ban you.
Yeah.
I mean, go
yeah,
listen
like what's
to
the problem of streaming a debate? Like as long as you don't share personal information.
Yeah, that's it. I mean, every server has this rule. You cannot record or stream debates, not even with permission. Not even with permission. So anyway, it's hopeless. So if you're a small creator, it's just a war against small creators. How dare you be a small creator? Like people who have big servers, they can record because they want to be able to record and make the content. They don't want you to be able to make content. Why should you make content? You shouldn't exist. So that's it. Anyway, Hamburger, we're reviewing Einstein's paper. We're losing our minds, but we're beginning to regain our minds slowly. Are you okay? Is everything okay?
Yeah, can you hear me?
Yeah, I can hear you.
I'm honestly kind of upset, but like we can talk about it later if you want to like stream your paper.
Yeah, I got it because Senis has to go to sleep soon, and I need his feedback, and I'll text you as soon as I'm done. I'll text you and I'll talk to you as much as you want.
That sounds good to me, man. Okay.
Excellent. I'll see you later.
Alright.
See ya.
See
See
you.
you
Bye.
if you're eating. It's
Okay,
probably
so
eating
let
the
me-
echo.
Wait, you're still hearing the echo?
No, she's probably eating my echo.
Oh. Anyway, let's share what do you call this? ChatGPT. Anyway, so yeah, so it's fine. I don't know if I should even mention Shankar. It's bad enough. It's whatever. Let's just I mean, the question is, should I make a big sensation? Why is it? I don't think I need to mention that it's a big deal that I'm disposing of the postulate because I'm proving it. Anyone who knows anything will see. Will see. You know, if somebody doesn't understand how powerful what I'm doing is, then so be it. I don't need them to. You know, I don't need
Yeah,
to
but
make.
the question is, you usually have to go into more detail in these things because people will, if it's too simple, people will just dismiss it as too simple.
If it's gonna get dismissed, then I'll just look. We're gonna write more papers. I don't want so each paper. I
Okay.
just want it to be. I don't want to have to start explicating and and making big speeches. I want it to be technical. We have so many papers in which we're actually going to disprove things that he said. This is like a tiny disproval of what he said. It's not really a disproval, you know. We're overriding him. We're saying everything he said is correct, but it's part of a bigger picture. It's very nice what he said. It's very nice what he noticed, but there is a bigger picture. Let's draw the bigger picture. That's my point. So I'm putting him in perspective. I'm diminishing his role as the God, the God Emperor, Lord Jesus himself. I'm bringing Einstein back into human form. So I think it's bad enough what we're doing. I don't think we need to do anything else. So in his paper, I will do an intro. In his paper, Albert Einstein, I would say, bases.
Yeah, you can do that later.
Okay, yeah, I'll do that.
That's not that important.
Okay, so for that, we will introduce a thought experiment based on the famous photon clock. No one, I mean, only maybe people from the internet know the photon clock, so we're not going to do that. All right. So this thought experiment will consist, so we're going to just introduce a thought experiment. So for that, we will introduce a thought experiment, period. This thought experiment will consist of a bathtub filled with water. In this bathtub, we will place a rubber ducky. This rubber ducky will measure, it's a state-of-the-art rubber ducky. So it's not, it's a technological, it's a rubber ducky with some technologies. We'll add, we will add some technological advancements to this rubber ducky. And this in the coming papers, but I don't want to talk about the coming papers. Just that we will add some technological advancements to this rubber ducky. So this rubber ducky will measure. So these technological advancements, using these technological advancements, this rubber ducky will measure the speed of the surface water waves in this bathtub. Using these technological advancements. Okay. This rubber ducky, and we can start saying the rubber ducky instead of this, because we already introduced the rubber ducky. Okay, the rubber ducky will be at times stationary and at times moving with respect to the water. Okay, we don't need to be a constant C. We will assume that the rubber ducky has a mechanical clock that is based on, okay, that's the next step, okay. So we'll come back to its motion. The point is that using these technological advancements, the rubber ducky will measure the speed of the surface water waves. Well, we already said it's. Did we say we will add some? Okay, did we put the rubber ducky in the water? Yeah, in this bathtub we will place a rubber ducky. So we don't need to say that it's in the water. Okay, using these technological advancements, the rubber ducky will measure the speed of the surface water waves. Okay, the rubber ducky will at times be this. Okay, let's go take this. So we will assume the rubber has a mechanical clock based on the waves themselves. Okay, so let's talk about. Okay, using these technological advancements, the rubber ducky will measure the speed of the surface water waves. So what is specifically? The way it's going to measure the technique. The technique
You don't need to add
employed.
more to that. This is like 100% fine. It explains everything that needs to be explained.
No, but I mean look. The abstract needs to. This is I'm getting into the details of the experiment. That's not good.
No, but you
Really,
shouldn't do that on the abstract. Like, that's not what the abstract is for. Abstract is just a synopsis.
right. So really, what I want to say is something. This like belongs already to the setup. So this is not for now. This is the setup. We'll come back to this. Okay. So really, what I want to discuss in the abstract is the bigger picture. So Einstein. So here it is. So in his paper, Albert Einstein.
No, that's set up for that to introduce a thought experiment. This is actually fine for an abstract experiment because it's describing your paper.
But it's
in like a very general way.
But look, the point of the paper is the bigger picture. Is to put the theory of relativity in perspective. That if you assume that the clock, what are we trying to do? We're trying to create an experiment in which the clock depends on the wave. So in any such experiment, that is the bigger picture, the biggest picture. Any clock, any experiment. So here's the bigger picture. So this is Einstein, but in actuality, there's a bigger picture. In actuality, there is a bigger picture. Special relativity is just a special case It's just a special case of the following. Of any experiment in which we measure the speed of a wave with a clock that depends on the wave, on such a wave, on such waves. That is the bigger picture. And in actuality, there is a bigger picture. Special relativity is just a special case of a larger set of experiments. These experiments include measuring
Nah, don't write that.
Why? What do you
In
mean?
actuality, there's a bigger picture. Special relativity is just a special case. No, special relativity is a theory. It's not a set of experiments.
No, it's not. This is what I'm saying. Special relativity is no longer. I'm demoting special relativity from a theory.
Yes, but that won't be taken in. Like that's like you have to understand. That's the first thing that someone will read in your paper. You want that to be the last thing that someone will read in your paper, not the first. The
But this
first
is
thing
what.
should be like telling them why you have an interesting experiment or something like that.
What do you mean? I need.
Yeah, because if you say that, it's going to be dismissed immediately by like 90% of people.
I don't need 90%. I need one. Like Einstein. Everyone dismissed Einstein except for Planck.
Well, yeah, but that's
I just
no,
need. Who's the
that's
biggest?
different.
Who's the biggest? Who's the biggest name today? I just need one big name to take it
No,
seriously.
are there any big names today? Kind of, like maybe
Sean.
Eric Weinstein or something.
Eric Weinstein? I don't know. He's not. He's not. He's nothing. He's not. No, I don't like him. I hope he.
You don't
He's
like
the
him?
last one.
I don't know.
I don't like him. He's into, like, he's basically a flat earther.
He's a flat earther. What? No, that's weird. I don't know. I don't know much about the guy. But,
I used to
I
respect
don't
him.
believe that.
No. He's not a flat earther. He's just no. I don't look. I
Yes,
it
I
does.
see. You're trying to call him like someone who's into weird theories.
He's into weird theories. Like I don't like his. He believes in nonsense, things that I consider nonsense,
What does he
unscientific.
believe in, for
I
example?
don't remember. I don't remember. What does he believe in? Oh, what nonsense does he believe in? Oh my God! Let me look it up 1 second. This is.
Okay, well, it doesn't really matter.
It doesn't matter.
If you
No,
remember
because
it, you can
I
say.
don't remember. I don't remember. I just remembered last time I heard him. I said to myself, "Okay, that's the end of that. I no longer. I don't respect him anymore as a scientist." Um, I don't like Keating. Sabine Hossenfelder, I don't like her. She's an asshole.
You
She's
don't like
oh,
her?
she's
Ah,
an she's okay, but she's an
she's
asshole.
fine.
She
No, I
always
don't
makes
like. I don't
fun.
like Keating. I don't think Keating is very honest. I don't like
Of
him.
all of them, I think he's one of the more honest.
No, I don't think so.
Look, Sean Carroll is okay.
I don't know who that is.
Neil deGrasse Tyson is not.
Neil is no, Neil is closed-minded.
Okay. I don't
Yeah,
like
not.
Michio. Michio. I don't like
Michu is
Michio.
crazy.
Yeah. And that's basically the end of the list. I never
There's
liked Hawkins, and I
the
never liked
what?
Hawkins. I don't like Penrose. Hawkins was terrible. Penrose is a
There
complete
is that
buffoon.
guy, the Wolfram. Wolfram, yeah, that's his
No,
name.
I don't like him. No, I don't like
No,
him.
I think he's a cool guy. So he's a nice dude.
No, I don't like him. He talks about his finite element, whatever. Like,
Yeah, he's too abstract. That's his problem.
I don't know what he's talking about. I never understand him. Anyway, look, some whoever. Okay, I'm gonna write more papers. This is just, this is just the tip of the iceberg. This is just the first one in a very long list. I mean, there's so many. I have so many good ideas that are very, very strong. Like this is like nothing. This is small potatoes, as they say in English.
Yes, but I'm talking in general even.
I
Like
can
you shouldn't
prove.
make like immediately.
I'm gonna write a paper proving the null result of the interferometer of Michelson. I'm
No,
gonna
but like
show
you have to check that better. You have to check that experiment that I sent you, the silver tooth experiment.
the silver. You mean
Silver
the
tooth.
silver tooth? What did silver tooth say?
Oh, I sent that to you on
The Miller?
days
Miller
ago.
experiment?
Yeah, he redid the Michelson-Morley experiment, and there are many others who did that.
I tried looking it up. There's no data. There's nothing. There's just a few
I gave you the
lines.
paper.
Which
Doesn't the
paper was
paper have
that?
the setup?
Let's look it up. Okay, you know what? But that's
Yeah,
look.
whatever.
I
Let's go another time.
no. What I'm saying is, one of my next papers is going to be let's prove why Michelson and Morley should have failed, regardless of anything you want to say. If you look at the numbers, they could never have been accurate enough to get anything but a null result.
Yeah, that's true. Their equipment wasn't good enough.
Exactly. So, and
But
then
I
I would,
mean, there surely are like papers on that already.
fine.
I'm sure
But if
about
you,
that.
you mean it, that's not very likely because if you
Really?
have a paper, if somebody did the research proving that they should have received a null result, then the next thing is let's build a normal piece of a normal
Well, I
setup.
mean, people can do that, but like in order to build a novel one, you need state funding, and you need to go through a lot of hurdles.
Not
That's
really.
easy.
Not
Yep.
really. Not a lot of funding. It's not like $1 million. You can do it like in a normal lab setting. You should be able to
Yeah.
put together
I mean, yeah, you could.
like these people have access to high power lasers that you need a high power laser, very accurate mirrors, and then you build a rig like with with a bunch of mirrors. Anyway, I'm not saying it's zero, but within a couple of thousands of dollars, you should be able to build, like a good setup, a good interferometer that should that over 90 degrees rotation should give you enough of the beginning of a wavelength, not a complete wavelength, but you should be able to move it back and forth and see statistically significant results. Let's say 1/10 or 1/100th or even one
Yeah,
thousandth.
the problem is making it precise. Yeah.
So if you have good
And if you're going to
sensors,
rotate it, it's a problem.
what?
If you're going to rotate it, it's problematic.
Okay, so that should not be the problem. It should be doable to rotate it.
Yeah, it's doable. It's just not that simple.
It's not that
That's the
simple, but
problem.
it's not like $1 million.
No, it's
Like
not a million dollars. No.
so for like 1,000 up to $10,000,
Yeah,
you
you just
should be
need
able.
like very high quality equipment. It's
Yeah,
gonna be a few thousands, yeah.
yeah. So like a normal, even a high school can do this. Certainly a university, someone
University
who's
can do this for sure.
this is a good PhD. So we should
Yeah,
we should we should
if it's
write
accepted.
out. I mean, you can. What do you mean? It should be doable.
Oh,
It should be
yeah,
doable.
it's always the problem. People are making this for money. It's not really for science. But anyways, let's continue the paper.
Let's continue. Okay. So special relativity is just a special case of a larger set of experiments. These experiments include measuring these experiments in such experiments we would measure the speed of a wave, the speed of waves. It doesn't matter in what, right? It's not just in fluids, right? It could be in air or in solid. The speed of waves. However, we will use a special clock for the time. However, we will not use any. Hold on, I have a message. Did you send me something? Oh, I need a vegan for a discussion later. Okay. Oh, sheep. I don't get it. Sheep? What? Who's sheep? Oh, sheep wants to debate. Okay. Alright. Where are we? Okay, so however, we will not use any, just any, use just any clock. Right, so we want to measure the speed of a wave. However, okay, so for that, the equation is speed equals distance divided by time. Time is defined by a clock. However, we will not use any clock or just any old clock or any clock technology.
No, don't write that.
Just any clock. The point is, I'm not using any clock. Rather,
You are using a type of clock.
right, but it's we would
So,
only use a very specific, not even special, a very specific clock. Not just any. This clock must depend on the very type of wave that it is used to measure. That's it. That's special relativity. Special relativity is just a special. Anyone who reads this paragraph will say, I know where he's going, he's right. Special relativity.
No, I think there's like one person in the world who knows where you're going with that.
Special relativity is just anyone who reads this is like, what do you mean? Special relativity is a case? It's a case of a larger set of experiments? It's not even the
Everyone's
theory.
gonna be like, nah, this dude, nah,
I need to say the
doesn't know what
theory.
he's talking
Here,
about.
let me say, the theory of special.
No, I wouldn't write that. I think your setup is just fine for an abstract.
No. Look, I have it. The abstract is not the setup. The setup is the setup. The abstract is the abstract. In the
Yeah, but
abstract, I need.
this is about the paper is about the experiments.
No, it's a thought experiment. It's not an experiment. I have nothing to say with this thought
Sort of.
experiment. I only want the whole point of the paper. Right, anyone who reads the abstract should be able to like the purpose of the abstract is that a person from the state of the art, from the art, should be able to figure it out and perform the experiment themselves. They don't need me. That's what an abstract should be. Someone from the art should be able to read the abstract and do everything on their own and replicate the experiment just from the abstract. It should be enough. And actually, they should not read anything else because they should be as objective as possible. The paper is just a report for anyone who does not want to reproduce. But anyone who wants to reproduce the experiment shouldn't read the paper. They should just read the abstract. So the theory
Yeah, that's why your setup is perfect.
No, the setup tells you too much. Wait 1 second, I have an important message. Let me check that. We can always rethink it. Let me just get this message.
Okay, let's continue.
Yeah, I just need
So
to
the
pick up a
setup is
message.
done.
One second. One second. Okay. Any other messages? No. Until when can you work? Can you work late tonight?
I can stay like half an hour more.
Okay. Yeah, because I want to go eat. I didn't eat my late supper yet, and I'm starving. Beginning to starve. Okay, so the theory, or maybe even Einstein, Einstein's theory of special relativity. We don't need this. Siri keeps attacking me. Einstein's theory of special relativity is just a special case of a larger set of theories. Of a larger set of what? It's a case of a larger set. I'm not going to say of what, because it's not even a theory. It's nothing. What is the larger set? In this larger set of what?
Put a larger picture.
No, but then the next statement I need to explicate that it's always about measuring the speed of a wave. It's just a case of a larger set, I guess, of experiments. In such experiments, we measure the speed of waves.
Yeah, I mean, but the first sentence is just kind of incorrect.
What's incorrect?
Like, yeah, I know what you want to express, but it's not going to be read like that.
What?
The
What did you
first
say?
sentence you need to put different. Just a case of a larger set.
We'll come back. We'll come back to it. I just need to, I need an outline. So, Einstein's theory of special relativity is just a special case of a larger set of experiments. Not without just. It's a special case of a larger set of experiments. So they're going to say, what is the experiment? It's not an experiment. The theory of relativity is not an experiment. So maybe Einstein's special relativity is a special case. It's just a case. Is a case of a larger set of experiments.
No, special case was fine.
I can't. You're not allowed to use the same word twice in a sentence.
Why?
It's a good rule.
I never understood that.
Yeah, it's a good rule.
In one case it's like it's not even really the same word. One case it's the noun, the other is an adjective.
It's a good rule. It's fine. I like that rule. Einstein's special relativity is a case of a larger set of experiments. And that is what we're here to say. So in this paper, what are you cutting? In this paper, we will prove that Einstein's special relativity is a case of a larger set of experiments. We will demonstrate. We're not going to prove anything. We'll just demonstrate. We will attempt to demonstrate. Are we going to do that? Yes, we are. Yeah, that is the only thing that we're going to do. In this paper, we will demonstrate that Einstein's special relativity is a case of a larger set of experiments. In such experiments, we measure, it's a family of experiments. It's a set. In such a set of experiments, we measure the speed of waves. For that, the equation is speed equals distance divided by time. Time is defined by a clock. However, we will not use in this set of however, we don't this is the set of experiments. However, in this set of experiments, we will not employ.
I mean, I think you're complicating this so much. Like, you should.
No, what do you mean? This is the thesis. There's no complication. This is the essence. This is the essence. Anyone who that I talk to and I tell them, they ask me, what do you do with your life these days? I tell them, this is exactly what I tell them. I tell them I'm just writing a paper to show that Einstein's special relativity is just a case in a it's part of a set. It's just, what do you call it when like every member? It's just a member in a set. The set is all the experiments in which we measure the speed of a wave, where the clock that we use depends on the speed of the wave. That is it. Now, and then we're going to explain why relativity happens to be that special case. Okay, we're not going to use any old clock. Rather, we would only use a very specific clock, namely one second, I have a message on the Discord. And the message on the Discord says, you're not rhetorically appealing. We are discussing inappropriate conversation tactics. We're discussing inappropriate. Wow, that is something I would like to participate in. I'd love to participate. That's amazing. That's a good topic. Okay. So
Yes, she's seen that.
Yeah, for sure. Yeah. That's like the most important, one of the most important things is inappropriate debate tactics. Okay, rather we
Yeah,
would,
and I mean, hopefully this is besides anything that's fallacious, because that's kind of just too obvious. But yeah, we'll see.
Yeah. Rather, we would only use a very specific clock. Namely, a clock, or this clock, must depend on the very type of wave that it is used to measure. The result of all such experiments, sorry, I have to pick up this message. You are. Wait, you don't see it. You don't see the comment.
I see it as well.
Oh, okay.
I can see your chat on the Discord.
Oh, okay.
Yeah.
It's funny. Okay, so
The
result
classic.
of, so what's incredible is the result of all such experiments is guaranteed by definition. It's by definition.
Yeah, it's tautological, basically.
It's tautological, yeah. The result of all such experiments is guaranteed by definition to give a constant speed of waves as measured by all moving observers. Anyone who reads it is gonna rip his clothes
Yeah,
off and run.
that's a good one. Like that's a good one.
They're gonna rip their
But
clothes
like the
off.
first sentence in this paper, we will demonstrate that some special relativity is a subset of a postulate that is true by
No,
definition.
that's
I
not.
think you should start with that. It's a subset of a postulate that is true by definition.
It's not a postulate. The postulate is an
It's not
assumption.
a postulate, yes. Is a subset is or cascades down from something that's true by definition. It has to be something like this.
Uh, I, okay, look, I cannot put everything in the first sentence. So,
No, but it cascades down from something that is true by definition. Like you rewrite this sentence to sound better. I'm not good at that.
well, I'll come back to it. I don't know if I want that. Because
But I
I'm
think
looking
that's
for.
the key issue.
Yeah, but I'm building up. We'll see. We'll come back. I don't want to. I don't want the punchline to be the first sentence.
Ah, it could
I
be.
I don't want to claim. Look, I'm not saying that it's a tautological, or I'm just saying it's definitional. Definitional is not. I wouldn't say it's tautological. It comes out of the definition. It comes out of this. Speed is equal to distance over time. If I had a three-line equal sign, speed is defined, right? For that, the equation, or it's right. It's the definition of speed. Anyway, it's the equation. The equation is maybe is such that we define for that we define instead of the equation, or we define speed by the following equation. For that, we define speed by the following equation. Speed is equal to distance divided by time. Okay. Time is defined by a clock. Oh, so far so good. However, in this set of experiments, we will not employ just any clock. Rather, we would only use a very specific clock. Namely, okay, there's too many setups. Rather, we would only use a very specific clock. Maybe, comma, namely, no, just, rather we would use a very specific clock, maybe dash. This clock must depend on the, no, it's going to be a run-on. Rather, we would use a very specific clock. What are you tapping? It sounds like you're playing ping pong. Anyway, let's go through this again. Okay, time is defined by a clock. Time is obviously. It's not defined, it's measured. You don't hear the tapping? You're like tick-tocking. You don't hear the tapping?
No, but I was hearing it on my headphones, but
You
I'm
don't
not
know
using
what
my
the
headphones
ticking
now.
is? So you mean it's me doing the ticking and maybe it's echoing off of you? But I'm not ticking. Maybe it's my
Yeah, I don't know.
keyboard? Wait, let me if I'm hitting my keyboard. No. It's coming from you. You're doing something. You're tapping something. Anyway, for that we define speed by the following equation. Not for that, just we define speed. Or speed is defined. Speed is defined by the following equation. Speed is equal to distance divided by time. Time is obviously measured by a clock. However, this, maybe without however, in this massive week of profits, in this set of experiments, we will not employ just any clock. Rather, we would only use a very specific clock. Maybe that's too much. Let's try this again. In this experiment, in this set of experiments, we will not employ just any clock. Rather, the clock must depend, or the technology, anyway, the clock must depend on the very type of wave that it is used to measure. Maybe the clocking. But anyway, we'll come back. The result of all such experiments is guaranteed by definition to give a constant speed of waves as measured by all moving observers. Okay, that's the first paragraph. Second paragraph. So Einstein, wait, is there? Okay, Einstein special relativity measures or deals with or measures or his postulate. Special relativity's second postulate what does a postulate do? Okay, which to this also introduce another introduces. A postulate introduces, which is only apparently irreconcilable with the former, namely that the light. Okay, I think introduces the notion. A postulate introduces a notion. Okay, share. Okay, introduces the notion. So Einstein's special relativity's second postulate introduces the notion. What? That the speed of light is constant for all moving and non-moving observers, for all moving observers. Well, assuming, so in his paper, his entire point is that light is an electromagnetic wave. In Einstein's paper, he introduces light as an electromagnetic or electrodynamic. I don't think he uses the term electromagnetic. It's electrodynamic. The name of the paper is electrodynamics. It's not electromagnetics. Like, even though it deals with magnetics too, but I don't think he uses the term electro. Only twice does he say, electromotive. Yeah, here it is, page 2, in which electromagnetic processes take place. But he calls it electrodynamic. How many times does he say electrodynamic? 16 times is electrodynamics. He calls Maxwell's electrodynamics. He doesn't call it electromagnetic. Because there is no magnetic force. Magnetism is just... magnetism is what do you call it? It's an artifact of relativity. It's because of length contraction, right?
Wait, I was a bit distracted here.
So magnetism is I'm just wondering.
Oh, the idea that magnetism is because of length contraction. Yes.
So that's why maybe that's why he doesn't call it electromagnetic. because there is no magnetism. It's only electrodynamic. The dynamic is the magnet. When an electron is moving, it has magnetic effects. So maybe Einstein already is predicting. But anyway, he calls it electrodynamics, but he also says electromagnetic, so it's fine. We only use electromagnetic. So he says on page 2, assign a velocity value to a point. Where does it come from? So it starts here. So the introduction of a luminiferous ether will prove to be superfluous in as much as the view here to be developed will not require an absolute stationary space provided with special properties. Nor...
Well, I mean, I would ask where are the fields then?
What?
I would ask where are the fields propagating?
I don't understand. What did you say?
I would ask Einstein, where are the fields?
Oh.
Yeah.
No, I don't want to argue with Einstein. I'm
Einstein.
I'm trying to quote Einstein at this point. I'm just trying to understand.
Yeah.
Can I use the word electromagnetic or electrodynamic? So let me just see. Provide with special properties, nor assign a velocity vector to a point of the empty space in which electromagnetic processes take place. Okay, whatever. I'm not sure what he means. Let's go back to our paper.
A velocity vector point is just...
No, he didn't say a velocity. Oh, velocity vector? What
Yeah, so
velocity vector?
velocity
Oh,
vector
velocity
to a point.
vector. Okay. To a
Yeah.
point. Like he's saying empty space doesn't have a velocity vector.
But why can't you have a frame of reference of empty space? And I never understood that part. Because you could still do that.
Because he says it's a vacuum.
Yeah, but you could still do that theoretically.
Look, in this... Right, but in this paper, it's fine. Look, it's fine. Look, this is what I'm claiming is it just so happens to be the case, but it's a special case.
Yeah.
I'm explaining. It's just a special case. There's nothing special. It's just a special case of a larger set of experiments. Meaning, special relativity is just a misunderstanding. That's all. It's just a misunderstanding. If this paper doesn't shock the planet, if the planet survives this paper, I don't know. I mean, I don't know.
The planets will survive.
The planet doesn't care. The planet
Yeah.
care. Well, the planet. Yeah.
Planet's too busy discussing if we should have genderless bathrooms or something like that.
Yeah. Right. Anyway, in Einstein's paper, okay, so Einstein's special relativity's second postulate. I mean, there's no way I would have been able to write this on my own because I would have killed my. This is so difficult to write. Einstein's special relativity's second postulate introduces the notion that the speed of light is constant for all moving observers. In Einstein's paper, right, that's the postulate. He introduces light as an electromagnetic or electrodynamic wave. Einstein agrees it's an I'm not sharing, 1 second. So let me go back to the page. Let me see the word wave 12 times. Let a spherical wave be emitted. It's only me and Einstein who claim that
Wait, we now have to prove that any ray of light measured in the moving system is propagated at velocity c. If, as we have assumed, this is the case for...
No, it doesn't matter. I'm just looking for the word wave.
Oh, okay.
I just want to see the word wave because I want to see if he says that light is a wave, or is it, or I mean the paper is about electrodynamics. So are you gonna say he doesn't? The first time he says wave is on page 8. What am I supposed to do with that? Well, okay, I don't need to because the first thing he says.
Wait, but I think he's starting to do the.
I don't care. I don't
the
need
things
it.
the thing that you're trying to do.
No.
He's starting to do that.
Look. That's all I need.
Give me that paper. Give me the link of that paper.
1 second. Okay, it's in the YouTube. Here it is. Oh my god, okay.
Is it in YouTube?
I put it in the YouTube, in the hash new YouTube videos. But it's also, I always put it in the, it's in the side chat too.
Okay. But it was on the YouTube stream.
Oh no, I didn't put it in the YouTube stream. Let me put it in the YouTube stream too. Alright, let's continue. So, my point being, I need to text Blush. I didn't text Blush. Let me text her. One second. What are you looking? What are you looking for?
I was looking for the where you were before. That had the tiles and okay, spherical. Okay, I found it.
What are you looking for?
Yeah, I have to read.
Oh, okay.
I was looking for the where you were.
Okay. Alright, so my point is that I don't need Einstein to say it's a wave because Maxwell's electrodynamics is that light is an electromagnetic wave. So it is known that Maxwell's electrodynamics, as usually understood at the present time when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. Okay. So, this paper is about electrodynamics of moving bodies.
Yeah, that's what we want.
What?
That's what we want. Exactly.
Right. So I would say that, I mean, he doesn't say explicitly that light is an electrodynamic wave, or does he? Let me look for the word wave. So we have 12 waves. Let me see. Just attained, okay, that's the second wave. By this wave, then, origin, coordinates, comment, let a spherical wave be emitted. He doesn't say wave of what. The wave under consideration is therefore no less a spherical wave with velocity propagation c. So he's referring to light as a wave. This shows that our two fundamental principles are compatible. Okay, whatever. Page 15, theory of Doppler principle and of aberration. In the system K, very far from the origin of coordinates, let there be a source of electrodynamic wave, which is a part of space containing the origin of coordinates, may be represented to a sufficient degree of approximation by the equations. Okay. So what is this electrodynamic wave? It's light. I hope. Wave train. Amplitude of the wave train. Wave normal. What is that noise? Construction of these waves.
Oh, that's probably wind. Yeah.
Oh.
That you're reading. Does that sound like tapping?
Why is it so windy? Where are? Oh,
Yeah, it's very windy where I am.
Where are you?
I am near mountains, so it's very windy.
Are you in Europe?
Yeah.
Where?
Where? I don't know if I should say that on YouTube.
No, I mean, just you can say approximately. I mean, I don't care.
I don't know. It's
are you
Southern Europe. Yeah.
Okay. Are you trying to be anonymous?
No, not really.
Okay. Okay, okay, let's see. We still have to find the amplitude of the waves. Okay. I mean, he talks about waves. He never says that light is a wave explicitly. Plane waves. This is the 12th time. So the first wave is on page 8, spherical wave of velocity c. Okay, he treats light as a wave. That's all I need. Okay, so in Einstein's paper, he introduces light. He doesn't introduce light as an electron. He treats light. He treats light as an electromagnetic wave. So in Einstein's paper, he treats light as an let me maybe create a separate paragraph like this. In Einstein's special relativity second postulate introduces the notion that the speed of light is constant for all moving observer. Okay. In Einstein's paper, he treats light as an electrodynamic wave.
Okay, there's one important part that you need to review on this paper.
Just before
because
that,
it kind of does the same thing more or less as you're doing with your rubber ducky on that part. That is search for this purpose we introduce a third system. Search for
one
that.
second. Let me just write one sentence.
It's on page 8.
Um, what should we look for?
Yeah, just go to page 8.
I'm on page 8.
Oh, okay. Wait, let me look at the stream. Go down. Okay, for this purpose we introduce no, not go down that much.
Okay.
For this purpose, introduce a third system of coordinates relatively to the system K is in a state of parallel translatory motion. So this is not very different from your rubber ducky.
What do you mean?
Yeah, it's not that. I mean, it's the same situation. You have two things in parallel motion.
I don't understand. What?
Okay, just read it.
For this purpose, we introduce a third system of coordinates k prime, which relatively to the system k is in a state of parallel translatory motion, parallel to the axis of whatever, such that the origin of coordinates of system k prime moves. What?
That's the x-axis, basically, I think.
This is the x-axis?
Yeah.
Okay, it moves with the velocity negative v on the axis, whatever. At that time, t equals 0, let all three origins coincide. And when t equals x equals y equals z equals 0, let the time t prime of the system k prime be 0. We call the coordinates measured in the system k, x, y, z prime, and by a twofold application of our equations of transformation we obtain. What's your, I don't, how is this the rubber ducky? Where does he say that? He doesn't know. This is exactly what I'm about to write. See, the next sentence is Einstein did not notice. I mean, basically what he informed the world of is he said he noticed basically a coincidence, or he didn't notice a coincidence. He noticed the effect, but it's just a coincidence. It just so happens to be that we measure that our consciousness works on light, and everything works on light. This is why it works out. This is the next statement I'm about to make. I can't believe no one noticed this. Jesus Christ, it's been 120 years. No one noticed this. Everybody's following him. Like when he wrote it, no one could have known. trying to think. Could anyone have understood it? I don't know. It's like they could because they didn't because Michelson failed. Even though Einstein says in 1950, I don't know if I told you, he's interviewed in 1950. He says, "I never heard about Michelson and Morley when I wrote the
Yeah, I
1905."
know.
He says,
I saw it.
I would have mentioned them in the paper, but I think he's wrong. This paper makes no sense if you like he says it on page 2 almost explicitly, verbatim, basically, that Michelson and Morley failed. I don't know. I think he misremembered during the interview. 1950, he's very old already. He's 50. He was 26 in '05. So basically 45 years later. So he's already 80. He's interviewed, he's already 80. 1950 plus 26 or 20, he's 70. 70 in those days, that's an old man. He's been through the war. He's been through a lot. He's misremembering his '05 paper. I think he's misremembering. He's misremembering. Because otherwise, how do you explain? It's right in the introduction. It's in page 1. Oh my God. Every time I click the page, it shifts to the off center. So it's in page 1. Together with the unsuccessful attempts to discover any motion of the Earth relatively to the light medium, besides Michelson and Morley, who else did that? In 1905?
Yeah.
Who else did that? It's only not only that, he's aware of Lorentz. Lorentz spent his entire life trying to figure out Michelson and Morley's failure. Einstein is supposed to be a student of Lorentz. Or something like that. I read that somewhere. So he was with Lorentz, talked to Lorentz, whatever. He gave his 1920 speech in Leiden in the Netherlands. That's Lorentz's university. So he knew Lorentz obviously on a personal basis. I don't know in 1905. In 1905 he was a nobody theoretically. So I don't know if he knew anyone, but he was obviously. You see from his papers. I mean, this paper. This is a good paper by any measure. It's a good paper. I mean, so obviously he was a great great thinker. He was able to confuse the entire scientific industrial complex. So how could he have not known about Michelson and Morley? It sounds unfathomable. He says, I would have mentioned them, but this is the mention. No one in those days put references. I don't think there's a references section at the end. There's no references. In conclusion, look at his in conclusion. It's 3 lines. In conclusion, I wish to say that in working at the problem here dealt with, I have had the loyal assistance of my friend and colleague M. Besso, and that I am indebted to him for several valuable suggestions. I never heard of Besso. That's it. That's Einstein. There's no references. He never referenced anyone. Did he reference Lorentz? Yeah. No. Well, that's one. I don't know who put this note here. Did Einstein? Probably this is Einstein. So Einstein, the preceding memoir of Lorentz was not at this time known to the author. So, wait, what? He didn't know about Lorentz? The preceding memoir? Wait, 1 second. What? They
Yeah,
suggest
supposedly.
they suggest rather that, as has already been shown to the first order of small quantities, what this is the second paragraph. Oh, this is right after this. So light medium suggest that the phenomena of electrodynamics as well as the mechanics possesses no properties corresponding to the idea of absolute rest. They suggest rather that, as has already been shown to the first order of small quantities, the same laws. What do you mean? What is he saying here? As has already been shown to the first order of small quantities? What is he talking about? The same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. The preceding memoir by Lorentz? What preceding memoir by Lorentz? I don't know what's going on. Who's writing what? Which author? Einstein? Who's number? Who made this footnote? So Einstein didn't even make any footnotes. So Einstein had no footnotes. So
No.
so he didn't mention anyone. Let me see. Lorentz. That's 4 times Lorentz. Let me see. The equation of the Lorentz transformation may. Oh, I'm not sharing? Oh, Jesus. I hate it when this happens. I'm not sharing. The equations of the Lorentz transformation may be more simply deduced directly from the condition that in virtue of these equations the relate. But who says this? Editor's note. Who is the editor? It's not Einstein. That's the translator. Look at this. In Einstein's original paper, we need to look at the German paper. The symbols, or these symbols, for the coordinates of the moving system K were introduced without explicitly defining them in the 1923 English translation, which is what we're reading. XYZ were used. No, we're not, because we don't have XYZ. We have this HZ. We're just creating an ambiguity between X coordinates and the fixed system K. Okay, whatever. Okay. Hopefully everything was resolved. Anyway, I'm beginning to feel starvation. So
Yeah, you wanna go?
I don't want to go. I want to continue. Let me just.
No,
what's your
but I need
schedule?
to go actually. Yeah.
What's your schedule? When can you come back? When can
And I can
when
come
can
back
I?
today.
What do you mean today? What is
No.
today? You cannot come. I mean, obviously not today. Today
Yeah,
for you
but
it's already
like,
midnight.
I'll have shitty internet until like Sunday
It's
afternoon.
good. Your
But
internet is good. I'm okay with your internet. The
yeah,
question is
okay, but
when.
I'll see if I can tomorrow.
Okay, text me when
If
you're
not,
ready.
Sunday.
Tomorrow night I'm going to a party. So
Okay, so Sunday.
no, but let me know whenever you're available. Let me know. I'm
Yeah, yeah.
available the whole day. Just at night I'm going to a party.
Okay, that's fine. I'll probably we can talk a bit during the day. Yes.
Okay. Okay, so text me when you're ready to go. All right, thank you, man. I'll see you.
All right. I still want to read this paper as well. It's
Fantastic.
interesting.
I never read it. I have no idea what he's saying. I don't care.
Yeah. Okay.
All right,
So
I'll see you.
nice talking to you as usual.
Yeah,
See
absolutely.
ya.
Yeah. See you. Bye. Okay, let me sign out of this room. Done that. Okay, so I think we're ready to quit. All right, it's good. We're moving along with the paper. Let me give you the link to the paper so you can write comments. Yeah, it's okay that you can see my email. Yeah, you can let me copy the link and you can have it in the chat. Here it is. Google Docs sharing. So there's the link. All right. It was a good 3 hours work. All right. See you next time. Bye.